Hello friends, so today we will discuss tutorial 7, which is basically dealing with MATLAB code for BR generation. We will evaluate BR performance of a spread spectrum BPSK system. Specifically, we are going to do it over a fading channel as against the plain AWGN channel which we had dealt with in the last tutorial. So this tutorial is specifically to evaluate the performance over a fading channel, and we will see what kind of fading channel we are going to consider. So as was explained in the previous tutorial as well, we begin with a modulating data source which will generate bipolar data from binary data, and the switches as explained was the operation of the switches are such that if it's on all the switches are on in position 1, then we have a conventional BPSK modulated system without spreading, whereas switching to 2 incorporates the spreading process and correspondingly the de-spreading process at the receiver. So we are going to analyze the performance of the spread spectrum system. So we are going to switch over to position 2, and then we have a spreading code generator which will be multiplied with the incoming bipolar data. So this as we shall see is going to be a Walsh-Hadamard code once again, and we are going to take a length of 4. We have a BPSK modulator followed by a channel, and this channel, to be very specific, is going to be a relay frequency selective fading channel. So the modulated signal is going to be distorted due to frequency selective fading, which is nothing but a type of distortion that occurs when the bandwidth of the signal is greater than the coherence bandwidth of the channel. Basically what it means is that the different frequency components of the modulated signal will undergo different gains. So the spectral property of the original signal is going to be modified by the channel. So it's a slightly more complicated fading process as compared to the relatively simple flat fading case where all frequency components of the modulated signal undergo the same gain. However, the fading amplitudes are different, but in frequency selective fading the distortion is more because the spectral properties of the modulated signal itself changes. So we add AWGN noise which is universally present at the receiver. Because of frequency selective fading, we need to employ an equalizer in order to mitigate the effects of frequency selective fading. So in our case, we are going to use what is called as the MMSC equalizer, that is the minimum mean square error equalizer, and finally after equalization we de-spread the signal using the same spreading code which was used at the transmitter, and we demodulate the signal as we had done in the previous case. So basically this diagram highlights the multipath fading effect that happens in typical wireless channels. So we can see that different versions or multiple versions of the same signal are received through different paths. For example, the path corresponding to the parameters a0 and tau naught, where a0 denotes the path gain and tau naught denotes the path delay between the transmitter and the receiver, is a line of sight path, whereas due to reflections from objects we have additional paths represented by parameters a1 tau 1 and a2 tau 2. So typically a wireless channel would inculcate more than one such paths, which is essentially the cause for distortion, and a simple filter implementation or interpretation of this effect can be in terms of this linear filter that has been modeled. So we can model this effect by introducing the corresponding delays and map this effect to this model and implement it in order to run our code. We assume that we will have some kind of integrate and dump kind of a detector which will be able to resolve these paths and sum them up in order to facilitate detection. Now, one of the advantages of using a spread spectrum system over conventional BPSK is, to a large extent, it can help mitigate multipath fading, because after all, the spreading process spreads the signal over a wide bandwidth, but the strong autocorrelation property of the spread signal or the spreading code can be made use of in order to mitigate the multipath effect. Essentially, what I am trying to say is, spreading basically gives you diversity, which helps in reducing the effect of multipath channel. So that is what is our objective, to find out the performance of such a spread spectrum system over a multipath frequency selective channel. So much of this code, at least the initial part and towards the end, is the same description that was there for the previous code that we had covered in the last tutorial. So I'll quickly go through it. We generate a certain number of samples, and we fix a certain number of iterations in order to average over these number of iterations in order to find our BER. We can vary this code length. We could make it 4, 8, etc. So in this case, we have set it to 8. Then we have a range of EB by N0 values from -2 to 12. We have the probability of the error probability, the average error probability, which can be which is expressed as a variable over here, and we are going to collect the number of errors and store it in this variable subsequently. Now the key parts of this code are, one is the generation of the frequency selective relay fading channel, and secondly the equalization and spreading despreading operation. So this first part over here deals with the generation of the channel. So we have typically a mobile communication channel would have what is called as an exponential power delay profile, and that is characterized by a decay parameter, which we have chosen a typical value of this exponential decay parameter to be 1.2. Of course, you could change this and play around. We have chosen 4 number of multipaths. Once again, you could change this, just like how you could change the length of the code and observe the effect. So these are parameter settings. The amplitude of this PDP is nothing but the square root of this decay profile. The Rayleigh distributed amplitude parameters are generated by taking the absolute value of 2 Gaussian random variables, which here is expressed as a complex Gaussian random variable, as you can see, So this is a standard technique in order to generate a Rayleigh distributed amplitude and ensure at the same time that the phase of these components, the Rayleigh components, are uniformly distributed over 0 to 2 pi. We generate the impulse response, which is not normalized because we need to do that subsequently, but the impulse response is nothing but the power delay profile amplitude which we obtained in line number 21 multiplied by this complex variable which has an envelope which is Rayleigh distributed. So we can see, and then we can of course normalize the impulse response by finding the channel power and dividing the previous impulse response that we had got by this channel power. So what we end up getting is a normalized impulse response of a typical Rayleigh frequency selective multipath fading channel, which in our case for this run of the code looks like this. So please remember that this is the impulse response normalized by channel power. So this is the plot that is in line number 28. The next part of the code basically deals with spreading. So we had already seen this in the last tutorial, so I will not go into the details. We are using as I said Hadamard code of length 8 in this case, but you could experiment with length 4 because I think that was what was covered in the last tutorial. Nevertheless, the idea is to generate a bipolar sequence and spread the data by multiplying the bipolar data with the spreading code that is chosen from the matrix Hadamard matrix basically, which is generated in line number 34. This part of the program, that is line number 41 to 60, deals with addition of noise, that is we generate the range of EB by N0 values. But importantly, what needs to be noted over here is line number 46, which now is not merely the addition of the signal with AWGN, which will come later of course, but prior to that, because it's a frequency selective channel, we convolve the transmitted data, that is the spread data, with the impulse response which was generated in the previous part of the code. So convolution process models frequency selectivity. So this is a key or important difference between this program or code and the previous one. We add noise as we had generated in the code in the last tutorial, so that part remains the same. Of course, the difference being that for EB by N0 we scale the noise factor by the length of the code, because as we had said, the energy gets spread over the chips, that is the code chips, whereas for SNR there is no square root length code term, because the power essentially remains same. There is no notion of time for SNR. So the convolved data is added with AWGN noise, and we calculate the variance of the noise which is to be used for the equalizer. So now at the receiver we use MMSE based equalization, and actually the description of this equalizer is beyond the scope of this tutorial. However, I will just tell you some important points. The parameters required to implement this MMSE equalizer is, first of all, we need to generate the ideal response that we would get if we would convolve the channel impulse response with the equalizer impulse response, and ideally that should look like a delta function if we need perfect equalization. So that operation, or rather that requirement of the delta function, is given in line number 72. Other than that, we need to specify the length of the equalizer in terms of its order or the number of taps. So normally we would choose the number of taps greater than the number of samples that we have for the impulse response. So that is what is chosen over here, that is in line number 66. You could increase this length and see the effect of equalization. I will cut it short and advise you to kindly go through this implementation of this equalizer by reading the theory from the book Filter Bank Transceivers for OFDM and DMT systems. So this book is written by the authors Lin Fung and Vaidyanathan. So it's basically a Cambridge University Press publication. So I would request you to go through the theory first for this MMSE equalizer, and you will notice that the implementation follows the theory very closely. So after this part is the equalization part, and we also do the synchronization. A certain number of bits initially of the convolution, and then subsequent equalization is discarded. That is for the sake of synchronization, and the received data, which is the equalized signal, is stored in the variable specified in line number 82. The rest of the code is similar to what we had discussed in our previous tutorial, wherein we consider the received signal vector, convert it into a matrix, take the Kronecker in order to generate the periodic or repeated code sequence, and we simply multiply the code sequence with the set of data corresponding to each spread bit, and then we despread the signal, sum it up, and we measure the errors, and we determine the probability of error. So this is pretty straightforward and was discussed previously. And the last part of the code deals with bit error rate plot versus EB by N0 in this case. So we see that there are two important diagrams over here. The first one highlights or depicts the performance of this DSSS system, that is the BR performance, with spreading over AWGN channel, which is usually the bound, and in a fading environment. So we clearly see that the BPSK BR performance with spreading over a fading channel is pretty close to that of an AWGN channel, but remember that is only because we have used the equalizer in this case, and we have also used spreading. So spreading in conjunction with equalization has managed this kind of performance. However, of course, if we were not to use equalizer, for example, then we would get a kind of a flat kind of curve. So this kind of curve is without equalization. So equalization is extremely important to start with, and when we employ equalization plus spreading, we are able to achieve a very good performance. The second diagram shows the performance BR performance comparison between the BPSK system with a code length of 4. So I would also advise you to plot the same for a code length of 8, because that is what we had done in our code. It should be better than this performance, so that is left as an exercise to you. But with a code length of 4, we see that with spreading we have a better performance in a fading channel. So here we have not shown the AWGN channel because that is already discussed in figure 5. So both these curves are to do with frequency selective Rayleigh fading channel, and we clearly see that there is a performance improvement when we use spreading as compared to when we don't use spreading. The only problem here is that it's difficult to quantify by what or rather by to what extent this performance improvement occurs, or to give a value to the gain. The simple reason being that there are two factors involved in we realizing this kind of performance. One is the effect of equalization, and of course the second one is the effect of the frequency selective Rayleigh fading channel. So there are mathematical tractability issues due to which there is no value that can be associated with the gain obtained in terms of the BR performance improvement. However, the improvement can clearly be seen between the BR performance of BPSK with spreading and without spreading in a Rayleigh faded frequency selective multipath environment. So this concludes tutorial 7. Thank you.